Hello, welcome to Chapter 12. The topic of Chapter 12 is primarily theorems, and of course theorems have a strong relationship to tautologies and contradictions, so it'll make sense to review those very briefly. So remember what you know about contradictions. Um, we've become familiar with some specific examples of those for use in the rule reductio ad absurdum, that is the negation introduction rule. You know that a contradiction is any statement of the form P and not P. Anything and its negation is a contradiction. Another way to define a contradiction is if any sentence in a natural language or some well-formed formula of language S that is necessarily false, that it's always false on a truth table. If you put it onto a tree, it'll always close off, etc. All of those things are ways of defining contradictions. And so anytime somebody expresses a contradiction, they express something false, whatever the circumstances. That's all pretty familiar. Tautologies, of course, are largely the reverse. The concept of tautology, again, it's simple when contrasted with a contradiction. Where a contradiction is necessarily false, a tautology is necessarily true. And some examples of tautologies in S include P or not P, if P then P, or P if and only if P. All of those things are tautologies. And of course, the two concepts are related. Okay, the negation of any contradiction is a tautology, and vice versa. There's the vice versa. Okay, and of course, all contradictions are also equivalent to all other contradictions. That's how they relate to those concepts there. Contradictions are also interderivable from one another. All tautologies are equivalent to other tautologies. And so since we're talking about proofs, we can start to prove some things are tautologies. So for example, if something is necessarily true, then of course it depends on nothing else for its truth, right? It just simply has to be true. It doesn't have to be true because of anything. It just is, okay? It's necessarily true. In other words, any tautology is then entailed by the empty set. Okay, and so we've been talking about entailment as being a relation between a set and a sentence. A set, sometimes the sets we've seen have had one member, two members, three members, sometimes four, but it's possible to have a set with no members. Any set with no members, we call that the empty set, and it's written in the symbol here with just like the, here, I'll turn on the little pen. This thing here is the symbol for the empty set, okay? And so any tautology is going to be entailed by the empty set, that is a set with no members. Because every tautology doesn't depend on anything for its truth, it is entailed by literally nothing, right? So literally nothing entails. That makes it sound worse. So it says nothing entails a tautology. It's rather that a tautology is entailed even by nothing, right? That's the sense in which we want to see that. Okay, so any tautology can be derived without any givens, right? You can just start with nothing on your proof and end up deriving a tautology. And this is the only tricky part about theorems at all is essentially starting with nothing, starting with. And so what we're going to be doing here is taking a look. Here is we don't have any beginning assumptions. We're going to be trying to derive P or not P from the empty set. That means we're just going to be starting with nothing. Any tautology is a theorem, so that we know it can't be false. So the idea is that we're going to try and assume it's false, right? We're sure to get a contradiction if we just assume it's false. This is how pretty much all proofs of tautology start. I mean, not all exactly, but most tautologies, or most theorems, as we're going to call them, are started with RAA. In this case, there's nothing else you can do, so you have to make an assumption. You have to put something on your proof, and there's nothing else that really makes any sense. Okay. And so what we're going to do is on line 1, which depends on only itself, we're going to have the negation of the thing that we want to prove. We're going to have not P or not P, and again, we're making an assumption for reductio, and we're pretty sure we can get a contradiction out of that. And so The second step here is actually the hard one, okay? And then as the text says there, once you've got it, you're on your way. Notice that if we assume P, you can easily generate a contradiction, and then the P will discharge into not P, which we'll use to get the contradiction that we will use to discharge number one, right? This is a really fun and very elegant proof of the very simplest of all tautologies. This is essentially the tautology that is the law of excluded middle, one of our fundamental laws of logic. And so we're going to assume P for the purposes of, again, a reductio, because we need to get a contradiction. But of course, this P is going to discharge into not P. Remember, you have to discharge your assumptions. So really now we need two contradictions, but we'll be able to get them. Okay, and so the next step is to sort of discharge number two, right, because it leads to a contradiction. So if you assume P, use disjunction introduction, right, to here, right, to get P or not P, because if P is true, then P or whatever is true. Then we can simply put these two together, line 1 and line 3, right? And that gives us our contradiction, and then we're going to be discharging this into its negation. Okay, and so that's what we get there. We get the not P, and we've discharged the assumption that we made at number 2. And now we can just essentially rinse and repeat. If P gave us a contradiction, well then not P is going to give us a contradiction as well. So notice what this says. This says not P or not P, right? It says neither one of these. So here we go. If not P is true, well, then we'll be able to, then P wedge not will be true. Okay, and then again we get this from 5, line 5, and disjunction introduction. And then we're going to put together line 1 and line 6 to give us our contradiction, and that will let us discharge this first assumption that we made, this assumption we made here on line 1, because that was also for reductio. Okay, and so then the next step is to simply discharge that thing at 1. And that'll discharge into the double negation, not P, which in the next line will simply drop. Okay, and then that gives us this, our result, this beautiful tautology, this theorem. And notice over here in the dependency numerals, there's nothing over there. And so what this shows is that P wedge not P is indeed a theorem. If anywhere on a proof you have a line that really does depend on absolutely nothing, everything that it depends on has been discharged. See, we discharged 1 here at line 8, we discharged 2 here at line 5, and that's it. It depends on literally nothing, and so we ended up deriving it from nothing. Okay, only a tautology can be derived from nothing, and all tautologies can be derived from nothing. So when you derive something from nothing in a proof system, we call that thing a theorem. And so all theorems are tautologies, and all tautologies are theorems. Okay. Now I said earlier that many theorems are proved by using a negation introduction or reductio. This is an exception because it's a conditional, you have to use conditional proof, right? And so what do? You want to assume the antecedent and then try and derive the consequent. And if you're thinking ahead a couple of steps, you're thinking, well, this one's going to be pretty easy. And in fact, you're right. If you're thinking that, give yourself a pat on the back. You're really catching on. If not, don't worry about it. Once you see it done, you'll say, ah, I see what I should have seen, and then that's good. Then give yourself a pat on the back for seeing what you need to see. All right, so again, we're going to start with an assumption because we don't have anything on the proof yet, and since it's a conditional, right? We, see it's conditional here. We have to assume the antecedent and then derive the consequent. All right, so we assume the antecedent here for conditional proof, and our consequent is P. Now, gee, how can we get P? Is P anywhere on the proof? As it says here, there it is. I see, there it is. Right, it's like those old student blooper math tests where someone gives them a complex geometric problem, says find x, and then they circle it on the diagram, say there it is, right? It's like that. So there it is. Okay, and so because we assumed P and then we derived P because P is P, we can now conclude if P then P, right? It's the shortest conditional proof ever. We just assume a thing. In fact, this is the law of identity, right? If you assume P, well then if P then P must be true because P is P, right? And so that's what sometimes they call this theorem. They call it sometimes the law of identity. If P then P. right? Things are what they are. So whenever somebody says it is what it is, right? This is of course a tautology, and there you go. So that's it. It's done. Okay. And so what I wanted to talk about a little bit is another way to think about validity, right? For example, we know that the set if P then Q and P will entail Q, right? That's just modus ponens. And that so that means that whenever if P then Q and P are true, then Q would have to be as well. So the sentence if P then Q and P, right, then Q, right, that should be a tautology. If we replace that entailment, if we replace this comma here with a conjunction and this entailment symbol here with a conditional symbol, we should get a tautology if the entailment really does go through. And so that means that this argument, essentially this expression of modus ponens, ought to be derivable from the empty set. That is, it ought to be a theorem, right? A modus ponens, because it actually really does work, ought to be a theorem of our system. And that would mean, again, modus ponens is, that's what I just said. Okay, so another way to think about equivalence is the way that we have to think about it when we set up our trees, right? We know that if P then Q and not P wedge Q are equivalent. And that means that they are true and false under all of the same conditions. And that means that if we put a biconditional in between those two things, that should end up as a tautology, again, if they are equivalent. And again, this is just exactly what we have to think about when we set up our trees to check for equivalence. And so again, that means that this material implication is what they call this equivalence between these two things. That should be derivable from the empty set. That is, material implication should be a theorem of our system. Likewise, any other kind of real equivalence, any of those equivalences with a biconditional in between, there should be a theorem in the system. And so that's something that we can use our proof system for. In proving theorems that are biconditionals, we can prove equivalence, right? In proving certain kinds of arguments, right? We can sort of prove validity, right? Or we can prove certain kinds of valid argument patterns. And one of the things about this is that it leads to some systems of logic that have actually a lot more rules than our system of proof has. The system that we've been working with, that's in the book, has an introduction rule and an elimination rule for each of the connectives, and that's it. Of course, there are other systems in other books, some of which involve more rules, and some of those rules are as follows. Some systems involve a rule called theorem introduction, where you can simply insert a theorem at any point in any proof, so long as you can then, so long as you could actually prove that it's a theorem. Sometimes what they'll do is they'll sort of attach an appendix and say this is a theorem because, and then they'll attach the proof that it is the theorem. But the idea is that because these things are just true, period, they don't depend on anything else for their truth, you really can't just put them into a proof. Sometimes they will make a very difficult proof much neater and tidier. Okay. Sometimes proof systems will involve some substitution rules so that you can do a little bit more with a little bit less work, right? So if you have a conditional and you need to get a disjunction out of it, you can just use the material implication rule to substitute the conditional for its equivalent form, or vice versa. Same with De Morgan's laws. If you have a negated a conditional and you want instead the negations of each of the disjuncts, or if you have a negated disjunction and want the negation of each of its conjuncts, you can just substitute that out. Those are De Morgan's laws. Same with association or distribution. If you just need to sort of switch some stuff around in terms of parentheses, you could use some of those rules. And again, those rules can tend to make a proof neater and tidier, but then there's more that you have to remember. There's more that you have to keep track of. There's, all sorts of things. So, yeah. Of course, none of these allow us to do proofs that we were not able to do before. I want to stress that. None of these proofs are necessary, right? In fact, you can do any given proof with even less than the rules that we have in our system. But but you don't need them. Okay, they do sometimes allow a proof to be a little bit shorter and sweeter, but of course then it's more to keep track of. You think to yourself, gosh, should I use material implication here? Should I use the rule of distribution here? If you remember what those are, it's more memorization. It's, I think, more creativity involved in making a proof than the system we have. The system we have is really designed to try and limit your choices to make it easier to do, I think. So, but of course, if you read other books, you read other see somebody else's proofs, sometimes they'll use rules like this, and you can use a rule like this if you know that it's a theorem, or you know that these things really are equivalent, and that's really what allows these things to be done. So, for example, this is a proof of I think it's if you look at the previous slide, it's I think this is association, no, this is distribution. And so I just went ahead and whipped this one up the other day. It's, as you can see, a bit long, so you might want to sort of pause your video, zoom in, etc. I really would encourage you to look over a proof of this kind. If you want it in a different format, just let me know, and I can certainly supply that if this is a little too awkward for perusing the proof. But the idea is that it starts with p wedge q and r, and then ends up. Notice this is for conditional proof, and so you do the conditional proof going this way, and then you do the conditional proof going the other way. In fact, so this is one way, and then this goes the other way, and then you can end up concluding this biconditional down here, and that's our theorem. That's distribution, and of course that's one kind of distribution. There's the other kind that is distribution over the and instead of the or. But the idea is that if you wanted to use some of these other rules, you could do this shorter. So, for example, you could just use the theorem introduction rule and just put in that last line, right? Then you're done, right? You've introduced a theorem. It's a theorem, okay? But of course, that's not proving that it's a theorem, and so there's a limited usefulness for that. You could use the rule of distribution, the nice substitution rule, and do this proof in like 8 lines, okay? But of course, using distribution to prove distribution is not all that informative either, right? It's not all that much of a good exercise. You could use material implication through sort of this section of the proof here, and that would shorten it up by half a dozen lines or so, and make it a lot simpler. And again, if you read through the proof and then you go back to look at, it's actually disjunctive syllogism is the one that would shorten this section of the proof. Disjunctive syllogism is if you have a disjunction and the negation of one of the disjuncts, you can conclude the other disjunct, right? That would shorten things up a little bit, but again, the proof can be done just fine with the rule set we have. These other rules don't necessarily make a proof any easier, I don't think. Sometimes they can make them shorter, but at the expense of giving you more to keep track of. And I think the more options you have at any given point, sometimes the more it feels like you're doing something that's kind of creative instead of really just following a set of rules, doing what needs to be done, and keeping track of a goal, and then an intermediate goal, and perhaps even an intermediate goal. And so again, the difference between a long proof and a short proof is really just the amount of paper used in all practical purposes. So anyway, the takeaways from this, right, in summary, is that all tautologies are theorems, and all theorems are tautologies. Tautology can be derived from nothing. That's what makes it be called a theorem, is if it can be derived from nothing. And some very important equivalences can be expressed as theorems, and some very important argument forms like modus ponens or modus tollens or disjunctive syllogism or any number of other things can be expressed as theorems. And if you can prove it's a theorem, you can prove that that's a valid argument form, or that really is a good entailment relation. And this is yet another reason why the material conditional has to work the way that it has to work, so that the way that the conditional operates can be used to mirror the entailment or validity relation. And so that's a very important thing for logic. That way we can use our system of logic to talk about logic, right? It's a very important thing for us to be able to do, as you'll see when we get into the later chapters of the book. So for now, just know that you can derive a theorem from nothing. You can start the proof with nothing. Usually the first step will be to make an assumption. If your theorem is a conditional, start with conditional proof. If it's a biconditional, well, you'll want to do one conditional proof, then you'll want to do the other, and then put them together using a biconditional introduction rule. If your theorem is not right a conditional, then you're going to have to start with a reductio. You're going to have to assume the opposite of, or assume the negation of what you're intending to prove, the negation of this tautology. You're going to derive a contradiction. Usually it's fairly straightforward, and then you're done. So that's how theorems work, and that's how to do those. And so take a look at some of the practice items, and well, have a good time in the meantime.